Welcome to this lecture on data collection techniques and image analysis/visual interpretation. In this tutorial, we will explore the fundamentals of remote sensing technologies and the principles of visual image interpretation.
Earth observation relies on a wide range of tools, including satellites and airborne technologies, which continue to evolve. These include older satellite missions, newer systems like Sentinel satellites, very high-resolution satellites, airborne laser scanners, and drones. The challenge today is not only collecting data, but also managing and analyzing the massive volume of information generated. To address this, remote sensing systems use advanced IT solutions, such as cloud computing and machine learning, to transform raw data into meaningful insights for better decision-making.
The term remote refers to something that is not in direct physical contact. Sensing means obtaining information or data, such as temperature, pressure, or images. Therefore, remote sensing is the process of acquiring information about objects or areas from a distance, typically using satellites or aircraft. Natural remote sensing refers to sensing that relies on natural energy sources, primarily sunlight. The target reflects or emits radiation, which is sensed and analyzed to extract useful information. This slide shows the example of natural remote sensing. This slide explains the process of artificial remote sensing. The Earth acts as the target, and satellite sensors capture information by sensing electromagnetic radiation reflected or emitted from the surface. The collected data is then transmitted to ground stations for analysis, where it is processed using computer systems. After processing, useful information is extracted and presented as satellite images or classified images, which help in identifying land use, vegetation, water bodies, and other surface features. Overall, the slide shows the complete workflow from sensing the Earth to generating meaningful output for decision-making. Satellite sensors capture data in different spectral bands using multispectral or hyperspectral imagers. These sensors measure electromagnetic radiation reflected or emitted from the Earth's surface. The electromagnetic spectrum includes visible light, infrared, and other wavelengths, and each wavelength range is called a band, such as blue, green, red, near-infrared, and shortwave infrared. The image shown here represents the electromagnetic spectrum, arranged from short wavelengths with high energy, like gamma rays and X-rays, to long wavelengths with low energy, such as microwaves and radio waves. The small highlighted portion in the middle represents visible light, which the human eye can see. Satellite sensors, however, can detect not only visible light, but also infrared and other wavelengths beyond human vision, allowing more detailed analysis of Earth's surface features. This slide explains different types of satellite sensors and how they capture data. Satellites use optical sensors that are sensitive to different parts of the electromagnetic spectrum. These sensors can be passive, which detect natural radiation from the sun, or active, which emit their own energy and measure the reflected signal, such as LiDAR and radar. The sensor uses filters to separate incoming light into different wavelength bands, and detectors record the intensity of each band as digital numbers. As the satellite moves over the Earth, it continuously captures data for each band. Finally, the data from these bands are combined to create composite images, such as true color and false color composites, which help highlight specific features of the Earth's surface for better analysis and interpretation. Now discuss about true color and false color composite. A true color composite uses the red, green, and blue bands. The image appears similar to what the human eye sees. Vegetation appears green, water appears blue, and urban areas appear gray or white. A false color composite uses bands outside the visible spectrum or rearranges visible bands. This enhances specific features. For example, healthy vegetation appears bright red, water bodies appear dark, and urban areas appear bluish or gray. FCC helps in identifying vegetation health and land cover types more effectively.
A satellite image is made up of tiny picture elements called pixels. Each pixel represents a specific area on the ground and contains digital values corresponding to reflectance. This slide shows the spectral bands of different Landsat sensors, specifically Landsat MSS and Landsat TM/ETM+. It lists the wavelength ranges each band captures, such as visible green, red, near-infrared, mid-infrared, and thermal infrared, along with their spatial resolutions. For example, Landsat MSS had 79-meter resolution bands, while Landsat TM and ETM Plus introduced improved resolutions, including 30-meter multispectral bands and a 15-meter panchromatic band. The slide highlights how newer sensors provide more spectral detail and better spatial resolution, improving the quality and accuracy of remote sensing analysis. This slide explains the concept of image resolution. Image resolution refers to the number of pixels in a unit area of a digital image and determines the quality and level of detail visible in that image. Higher resolution means more pixels and clearer, more detailed images, while lower resolution results in fewer pixels and a blocky or blurred appearance. The images shown at the bottom demonstrate this difference, where the first image appears sharp and detailed, and the last image looks pixelated due to lower resolution. This slide introduces the different types of image resolution in remote sensing. There are 4 main types: spatial resolution, which refers to the size of the smallest object that can be detected on the ground; temporal resolution, which indicates how frequently a satellite revisits and captures images of the same area; spectral resolution, which relates to the number and width of wavelength bands a sensor can detect; and radiometric resolution, which represents the sensor's ability to distinguish slight differences in energy or brightness. Together, these resolutions determine the overall quality and usefulness of satellite imagery. This slide explains spatial resolution in remote sensing. Spatial resolution refers to the pixel size of a satellite image on the ground. It determines how much area one pixel represents. High spatial resolution, such as 0.41 to 4 meters, means each pixel covers a small area on the ground, so the image appears clearer and more detailed. Low spatial resolution, such as 30 to 1,000 meters, means each pixel covers a larger area, resulting in less detail. The diagrams show that when pixel size is 30 meters, one pixel represents a 30 meter by 30 meter area, making small features unclear. As the pixel size decreases to 5 meters or 1 meter, the image becomes sharper because each pixel represents a smaller ground area, allowing finer details to be identified. This slide explains temporal resolution in remote sensing. Temporal resolution refers to the revisiting frequency of a satellite over a specific location, meaning how often it captures images of the same area. High temporal resolution means the satellite revisits frequently, typically within less than 24 hours to 3 days, which is useful for monitoring rapid changes like floods or crop growth. Medium temporal resolution ranges from 4 to 16 days, while low temporal resolution means the revisit time is more than 16 days. The timeline shown in the diagram illustrates how satellites capture images at different time intervals, helping analysts track changes over time. This slide explains spectral resolution in remote sensing. Spectral resolution refers to the ability of a sensor to detect small differences in wavelength and the number of spectral bands it can record. High spectral resolution means the sensor captures data in many narrow bands, such as hyperspectral sensors with around 220 bands, allowing very detailed analysis. Medium spectral resolution includes 3 to 15 bands, typical of multispectral sensors, while low spectral resolution may have only 1 or a few broad bands, like panchromatic imagery. The diagram shows that as the number of bands increases from panchromatic to multispectral to hyperspectral, the ability to distinguish surface materials and features improves significantly.
This slide further explains spectral resolution using a black and white image as an example. A black and white image is captured using a single sensing device, and the pixel intensity represents the combined intensity of all visible wavelengths, blue, green, and red. Since all colors are merged into one band, we cannot distinguish actual colors in the image. That is why, in the example shown, we cannot tell the true color of the platform top or the girl's sash. This demonstrates that low spectral resolution, such as panchromatic imagery, provides less information about surface materials compared to multispectral or hyperspectral images, which capture separate wavelength bands.
This slide continues explaining spectral resolution using a color image as an example. Unlike a black and white image, a color image requires at least 3 sensing devices or bands, red, green, and blue, RGB. Each band captures a specific portion of the visible spectrum. When these 3 bands are combined, they produce a full color image. This means that higher spectral resolution adds more information, allowing us to distinguish actual colors and surface materials. In this example, because RGB bands are sensed separately and then combined, we can clearly see the true color of the platform and the girl's sash, demonstrating the advantage of increased spectral resolution. This slide explains radiometric resolution, which refers to a sensor's ability to detect small differences in brightness within a pixel. It depends on the bit depth of the image. Higher bits mean more gray levels and better detail. For example, 8-bit images show 256 gray levels, while lower bits show fewer shades. As bit depth increases, the image becomes smoother and more detailed.
This slide explains electromagnetic radiation, EMR. EMR is a form of energy that travels at the speed of light in a wave-like pattern. It consists of both electric and magnetic fields, which move perpendicular to each other. EMR is emitted and absorbed by charged particles and is the basic energy source detected by remote sensing sensors. The diagram shows how the electric field and magnetic field oscillate at right angles while moving forward through space.
To understand remote sensing, we must know the properties of electromagnetic radiation, or EMR. EMR consists of 2 perpendicular components, an electric field and a magnetic field that travel together at the speed of light, 3 × 10⁸ meters per second. It has 3 key properties: velocity, frequency, and wavelength, which are related by the formula V = F lambda. The diagrams show how these waves move and how wavelength and frequency are interconnected. This slide explains the electromagnetic spectrum, which is the full range of all possible frequencies and wavelengths of electromagnetic radiation. It includes gamma rays, X-rays, ultraviolet, visible light, infrared, radar, and radio waves. Visible light is only a small portion of the spectrum. Energy is higher at shorter wavelengths and lower at longer wavelengths. Remote sensing sensors use different parts of this spectrum to collect information about the Earth's surface. This slide explains different spectral bands of the electromagnetic spectrum and their uses in remote sensing. Blue and green bands are useful for water and vegetation studies. The red band helps in identifying vegetation types and man-made features. Near-infrared is mainly used for detecting healthy vegetation. Mid-infrared is useful for soil moisture and forest fire studies. Thermal infrared measures emitted heat energy for temperature-related studies. Microwave bands are used for terrain mapping and object detection, even in cloudy conditions.
Now, move on to visual interpretation or image interpretation. Image interpretation is the process of carefully examining images to identify objects and understand their importance. In remote sensing, it helps extract both qualitative and quantitative information from photographs or satellite images. It involves identifying natural and man-made features such as points, lines, and polygons on the Earth's surface. The interpreter analyzes patterns, spatial relationships, and characteristics to detect, measure, and evaluate environmental and cultural features.
This slide explains the basic principles of image interpretation. An image taken from air or space shows the pattern of the Earth's surface. These patterns represent physical, biological, and cultural features of the landscape. Similar conditions usually produce similar patterns, while different conditions create different patterns. The quality of interpretation depends on the analyst's knowledge, experience, methods used, and understanding of limitations. Let us understand the elements of image interpretation in a systematic way. Interpretation begins with primary elements such as location and tone or color. It then moves to secondary features like size, shape, and texture, followed by tertiary elements such as pattern, shadow, height, slope, and aspect. At a higher level, analysts consider site, situation, and association. As complexity increases, interpretation also uses collateral data, convergence of evidence, and multi-concept analysis to ensure accurate results.
Let's begin with the concept of shape in image interpretation. Shape refers to the general form or outline of an object seen in an image. Objects can appear linear, circular, rectangular, triangular, or irregular. Regular, straight-edged shapes usually indicate man-made features, like buildings, roads, or agricultural fields, while natural features, such as forests, tend to have irregular shapes. For example, irrigated crop fields often appear circular due to rotating sprinkler systems.
Now, let's understand the element of size in image interpretation. Size refers to how large or small an object appears in an image, and it mainly depends on the image scale. Interpreters compare the size of a target object with surrounding features to understand its significance. For example, large buildings in an area may indicate industrial or commercial use, while smaller buildings usually suggest residential areas. Both absolute size and relative size are important for correct interpretation. Let's explain pattern. Pattern refers to the spatial arrangement or repetition of objects in an image. When similar shapes, tones, or textures are arranged in an organized way, they create a recognizable pattern. For example, evenly spaced trees in orchards or regularly aligned houses and streets in urban areas form clear and identifiable patterns. Now let's understand tone and color in image interpretation. Tone refers to the relative brightness or darkness of an object in an image, while color represents the visible hue. Tone is one of the most important elements for distinguishing different features on the Earth's surface. Variations in brightness help identify differences in shape, texture, and pattern. The level of light or darkness depends on how much energy a feature reflects within a specific wavelength range.
Another important element in image interpretation is texture. Texture describes the arrangement and frequency of tonal variations within an image area. It can be smooth or rough. Smooth textures show little variation in tone and are usually associated with uniform surfaces like water bodies, grasslands, or paved areas. Rough textures show frequent and abrupt changes in tone, such as forests or built-up areas with irregular structures. Texture is especially important in radar imagery for distinguishing different surface features. An additional key element in image interpretation is shadow. Shadows help identify the shape, profile, and relative height of objects, making tall features like buildings, towers, or trees easier to recognize. However, shadows can also hide details because objects within shadowed areas may become unclear. At the same time, shadows are very useful for highlighting terrain features and landforms, especially in radar imagery. Another important element in image interpretation is site. Site refers to the geographic or topographic location of an object. The location itself helps in identifying features, especially vegetation types. Certain plants or land uses occur only in specific environments. For example, some tree species grow on well-drained uplands, while others are found only in particular geographic regions. Thus, understanding the site helps in accurate recognition and interpretation. Another key element in image interpretation is association. Association means identifying a feature based on its relationship with nearby objects. Some features are commonly found together, so recognizing surrounding elements helps in identification. For example, commercial areas are usually located near major roads or transportation routes, while residential areas are often associated with schools, playgrounds, and sports fields. Thus, understanding surrounding features improves accurate interpretation.
Resolution refers to the level of detail visible in an image. Higher resolution allows smaller objects to be clearly identified, while lower resolution makes features appear blurred or pixelated. If objects are too small or have low contrast with their surroundings, they may not be easily interpreted. Image quality, color, and overall condition also affect how accurately an image can be analyzed and interpreted.
That brings us to the end of today's session. I hope this video helped you clearly understand the concept and its practical importance in remote sensing and image interpretation. If you have any questions, feel free to write them in the comment section below. If you found this video useful, please like, share, and subscribe to the channel for more academic content from CoE Assam. Thank you for watching, and see you in the next session.